Quantitative Data Analysis Techniques 4.5.3. Range is the difference between the minimum and the maximum. For standing vertical jump, the maximum score was 56 and the minimum was 15. Therefore, the range is 41 as you would subtract 15 from 56. The higher the range, the further the values are spread apart, which shows how significant the difference is between the maximum and the minimum. For standing vertical jump, the range shows the difference in abilities for leg power. If the range for standing vertical jump was very high, then it would show that the abilities in the group of people vary a lot. The range is easy to work out and is a good option for ordinal data. However, the range can be heavily affected by outliers as it only looks at the highest and smallest values, which could be very different compared to the rest of the data. The interquartile range is the middle 50% of a set of data. The interquartile range ignores extreme values, unlike the range, which makes it slightly more reliable. It is used to show the dispersion within the middle chunk of the data to see if the results are similar or not. However, it is harder to calculate than the range, and it doesn't take into account all of the data, which means important results may not be analysed. If amounts of values are odd, then scores must be put into rank order, and then the upper quartile is 3 times n plus 1 divided by 3, and the lower quartile would be n plus 1 divided by 3. If amounts of values are even, put numbers into rank order and then separate them down the middle. On each side, identify the middle number, and then the lower quartile will be the middle number on the left, and the upper quartile will be the middle number on the right, as shown below. For my set of data, the lower quartile was 22 and the upper quartile was 49. Inferential statistics. William Trochim, 2006, states that we use inferential statistics to make inferences from our data to more general conditions. Basically, what this means is that you are trying to find a conclusion that is more than what the data is showing through inferring new ideas that could have a possible correlation to the results. The null hypothesis means that you believe that there is no significant difference in the data. You must always assume the null is correct until proven wrong. If there is a significant difference, then you are able to reject the null, but if there is no significant difference, then you fail to reject the null, as there is no significant finding. Alternate hypothesis is the opposite of the null, as you believe there will be a significant difference, and this can be directional or non-directional. Statistical tests are used to infer meaning from the data and to show the level of significance in the data. Statistical significance is the level of significance of the p-value, which represents the probability of a given event occurring. Statistical significance is affected by the sample size. P-values are calculated to see if there is or isn't a statistically significant difference or correlation so that the null can be rejected or failed to reject. There are two levels of statistical analysis. The first is to see if there is a difference between the means of the two sets of data, because if there is, it infers a difference. The second level of analysis is to see if the difference is statistically significant, as it will give more meaning to the findings, as the difference may be important for the study. You would also see if there is a relationship between the data sets by finding the correlation coefficient of the p-value as they infer a relationship. You would then see if the relationship is statistically significant by finding the p-value. There are 4 tests that are used, which are Spearman's rank order test, Pearson's rank order coefficient test, the independent t-test, and the dependent t-test. When choosing which test to use, you must think about a number of factors. One thing you should think about before determining the appropriate test to use is the type of analysis that will be used. You would then decide if you are trying to find a difference or a correlation so that you can think about what test will help you find out what you're looking for. If you're looking to find a difference, then you would use the dependent or the independent t-test. But if you were looking for correlation, then you would use either Spearman or Pearson's rank order test. Normality is another factor, as if the data is normally distributed, you would use a parametric test, but if it was not, you would use a non-parametric test. Parametric tests are used for continuous data like interval and ratio, and more powerful than non-parametric tests, as they are more likely to detect true differences or relationships that exist. An example of a parametric test would be Pearson's rank order correlation coefficient test, and a non-parametric test would be Spearman's rank order test. Research design is another thing to consider when choosing the test, as you need to think about whether it will be dependent, which means repeated measures will be used on the same group of participants, or independent, which is when you would use two different groups of participants. You must then think about the level of data, as the data will either be nominal, ordinal, or continuous. For nominal data, in the forms of counts, the chi-squared test can be used to assess the significance of the discrepancy of the results that were achieved and the results that were expected. If the data is ordinal, then you should use either Spearman's or Pearson's rank order test. If the data is continuous, then you would use Wilcoxon test, the Manny-Whitney U test, the independent t-test, and the dependent t-test. However, to use these tests, other factors need to be thought about. Firstly, to use these tests, you must be testing for difference, as they will not help you to find correlation in data. There must only be two categories, as using the four tests in the white boxes will not work if there are more than two. If the same subject or sample is used in both categories and parent population is assumed normally distributed, you would use the dependent t-test or paired sample t-test. However, if the sample is used but no assumptions are made about the parent population, you would use the Wilcoxon test. On the other hand, if a different sample is used and the parent population is assumed normal, then you would use the independent t-test, as more than one group of people must be tested on. If a different group is used but no assumptions are made about the parent population, then you would use the Mann-Whitney U test. Because the data is not normally distributed in the Mann-Whitney U test and the Wilcoxon test, it means they are non-parametric, whereas the independent and dependent t-tests are parametric, as the parent population is assumed to be normally distributed. This is the decision tree when testing for correlation. It shows that when both the variables are dependent and there is no causal relationship, you are able to use Pearson or Spearman's test. However, to use Spearman's test, no assumptions can be made about the parent population, which shows it is a non-parametric test. If the parent population is assumed to be normal, then Pearson's rank order correlation coefficient test can be used, as it is parametric. This is Spearman's rank order test. The aim of this test is to find the R value, as this will infer a relationship if there is one. The formula to work out R is 1 minus 6 times the sum of the differences squared over the number of participants times by the number of participants squared minus 1. This is shown in the top right hand corner. In my example, the number of participants is 14, which gives me an n value. You will then have two sets of data for the same group of people, and you need to put their scores into rank order, starting from the smallest. Once this is done, you look at each row and find the differences between each person's rank by taking one away from the other. If the difference is smaller, there is more of a correlation, as the results do not vary. After you have found the differences of each participant's ranking, you must find the sum of the differences, which was 0 for me. Next, you need to square each difference, so if the difference was 7, you multiply it by itself to give you 49. Then you must find the sum of the squared differences, which was 332 in my case. You now have all of the values that are needed, so you just need to put it into the formula. This gives me 1 minus 6 times 332 over 14 multiplied by 14 squared minus 1. This gives me an R value of 0.27. The degrees of freedom for this test is n minus 2, so the degree of freedom would be 12. The critical value is 0.59, which tells me that there is no significant relationship or correlation, as the calculated value is lower than the critical value. This is Pearson's rank order correlation coefficient test. The formula for this test is displayed in the top right corner, where n is the number of participants and x and y represent two different sets of data. In my example, the n value is 14, as there are 14 participants. You must then take the x values and find the sum of this, which was 116, and then find the square of this number, which is 13,456. You must then repeat this for the y values, which gives 115 for the sum of the values and 13,225 for the squared value. You must then square each of the x values and then find the sum of the numbers, and then do this for the y values as well. Finally, you must take each participant's x and y values and times them together, and then find the sum of these numbers. You now have all the values needed for the formula. This gives us 14 times 1020 minus 116 times 115 over the square root of 14 times 1290 minus 13,456 multiplied by the square root of 14 times 1057 minus 13,225. This gives me the R value of 0.35. The degree of freedom for this is n minus 2, so the degree of freedom is 12, and the critical value is 0.5324 when the level of significance is 0.05. This tells me that there is no significant correlation as the R value is smaller than the critical value. The R value gives the size and direction of the data. This is the independent t-test. The formula for this is mean 1 minus mean 2 over the square root of the standard deviation for dataset 1 squared over the number of participants plus the standard deviation for dataset 2 squared over the number of participants. Firstly, what you have to do is work out the mean of both sets of data by adding all the values up and dividing it by the amounts of values there are in each set of data. This gives me 8.29 for mean 1 and 8.21 for mean 2. Next, you need to find out the standard deviation for each set of data by using the formula in the top right hand corner. This gave me 5.03 for standard deviation 1 and 2.94 for standard deviation 2. I now have all the values needed so I can put it into the formula. This gives me 8.29 minus 8.21 over the square root of 5.03 squared over 14 plus 2.94 squared over 14. This gave me a t-value of 0.05. The t-value measures the difference in mean values relative to the variation in your sample data. The degree of freedom for this is n1 plus n2 minus 2, which gave me 26. The critical value for this test is 2.056 when the degree of freedom is 26, and the level of significance is 0.05. This tells me that there is no significant difference as the t-value is smaller than the critical value. The t-test tells us there is a statistically significant difference between the mean values of two data sets. The independent t-test is only used when two different samples are used and the parent population is assumed to be normal, which shows that it is a parametric test. This is the dependent t-test. The formula for this is the sum of the differences over the square root of the number of participants times by the sum of the differences squared minus the sum of the differences squared over the number of participants minus 1. There were 14 participants in my sample, which gives me the n value. Next, you must find the sum of each dataset's values, which gave me 518 for pre-training and 606 for post-training. Then you work out the difference between the scores by subtracting the smaller value from the bigger one. You then need to find the sum of the differences. After that, you need to square each of the differences and then find the sum of the squared differences. I now have all the values needed so I can put it into the formula. This gives me 88 over the square root of 14 multiplied by 666 minus 88 squared over 14 minus 1. This gave me the t-value of 7.98. The degree of freedom for this is n minus 1, so the degree of freedom is 13. The critical value is 2.160, which tells me that there is a significant difference as the t-value is higher than the critical value. Dependent t-tests are used when the same group is being used to try and see if the chosen variable has had an effect on the way they behave or perform. This test is also parametric, which means that the data is assumed to be normally distributed.